So in a single video now, we're just going to have a look at a rather odd entry in the catalogue of cognitive neuroscience. This is the work done by Walter Freeman on the olfactory bulb in the rabbit. And it combines a very profound philosophical sensibility, as Walter Freeman definitely had, with insights that are only available through the formal products of dynamical systems theory. It inevitably means that he's addressing problems of, I won't say perception or sensation. Our words are poor here. He wants to understand how the rabbit's neural system responds to familiar and to new odors by looking at the nervous system itself. So at the start of this course, we met Warren McCulloch, another very, very deep thinker. And he had suggested that one might identify the spike running down the axon with a logical bit, which allowed the brain to perform computation. And this inspired guess birthed a phenomenally huge set of developments in neuroscience, cognitive psychology, even in information science, and in the popular imagination. That one leap was very profoundly affecting. But not everyone followed Warren McCulloch in that, and there's lots of reasons to be unhappy with this, and we've taken some distance in ourselves from the neural parallels to elements within connectionist models. Around the same time, the EEG was available as a signal, a diffuse and messy and unorganized signal recorded at the scalp. Now, to measure an EEG is relatively simple. You apply electrodes to the scalp and measure varying electrical activity. But figuring out where that came from or making any causal story around that is extraordinarily difficult. And again, we find the true believers and the true skeptics. To the true believers, this provides a way of reading thoughts. But to the skeptics, it's quite clear that the signal is garbage. It is a miserably poor signal. Walter Freeman avoided both of these extremes, and he went for a scale as dictated by the technologies of the time, and we're talking work here mainly in the 80s and 90s. He wanted to study at a middle scale, a mesoscopic scale. So he looked at the activity of several thousand neurons within a fairly self-contained cortical structure, the olfactory bulb of the rabbit, which looks like this. That's on the left, the brain of the rabbit, on the right, the brain of the dog. You can see a big difference between them. The dog's brain has more of those folds in the neocortex that we associate with our own brains. The rabbit's brain is relatively smooth. Our olfactory bulb is lamentably small, but the rabbit has a well-developed olfactory bulb. Oh yeah, rabbits like some smells. So he had the ability to record from thousands of neurons simultaneously. And it was obvious to Freeman at beginning this work that the olfactory bulb is not a passive element. It's always active. There's always a dynamic involved. It's always busy. And measuring neural activity from the olfactory bulb, from these thousands of neurons, in the absence of any pheromonal stimulation, produced a signal which had all the hallmarks of chaos. And we've met chaos several times. But when a specific pheromone was presented to the rabbit, these neural dynamics simplified. They became more coherent, and the behavior of the olfactory bulb fell into one of many possible attractors. So we're dealing here with a very complex dynamical system in which the state space is going to be very, very complicated, of course. And within that state space, there will be multiple attractors. But in the absence of a pheromone, it's in a chaotic state, and in the presence of a pheromone, it falls into one or other of these attractors. Now, it's necessary here to dissociate this work from any sort of imagistic notion of the brain taking in information and processing it. That's not the framework being employed here. Instead, the role of the pheromone is to perturb an endogenously active system. So we've seen that when a system has its own endogenous activity, It can be perturbed, it can be kicked or poked, or punched, or presented with a nice smell. But the response of such a system is dependent on the internal organization of the system, on its history. And so in this sense, you're perturbing a system which is dependent on the previous scent world of the rabbit, on the life world of the rabbit, on its history. And the pheromone comes along and disturbs this this endogenous activity, causing the overall activity to simplify. We met just such a simplification when we studied the logistic map. Here we're showing the layout of the attractors somewhere between 3.7 and 4, and you can see that there's a clear region here where the behavior of the system for certain critical values of the parameter R simplifies. It goes from a chaotic form of organization to a much more coherent form. Measuring, describing, interpreting neural data at this mesoscopic level was entirely new. Furthermore, the tools that were used were quite foreign to cognitive neuropsychologists. And the consequences of this shift are still making themselves felt. It's my belief that Freeman's work opens up avenues that have yet to be fully explored. Part of this belief comes once more from Freeman's decision to employ what are the most successful tools we've ever used in science, differential equations, and to eschew, to do without fanciful romantic interpretations of what the brain is doing. He was very, as I said, his thinking was inspired not only by the froth of the last 5 years of neuroscience paper, but by a long history of philosophy and indeed theology, a bit like Warren McCulloch in that respect. He had reason to be sensitive to history. His father, also called Walter, was notorious in the field of neuropsychiatry for inventing the lobotomy. We won't blame the sins of the father on the son here, though. In today now, in biologically oriented cognitive neuroscience, as opposed to psychologically oriented neuroscience, studying the collective dynamics of ensembles of neurons using these kinds of concepts is becoming standard operating procedure. And rather than me lecturing on it, I think I've just taken this excerpt from an article by Scarda and Freeman that describes the role of chaos within the system that they observed. I'll allow you to, it's very boring to watch someone else read it, but I'll point out that he distinguishes between cases where the pheromone is known and where the pheromone is novel. When it's known, the system, which is in a chaotic state, collapses into one or other of the pre-existing attractors. But when a novel odor arises, then instead of producing one of these previously learned activity patterns, instead of falling into one of the attractor, the system falls into a high-level chaotic state, and this allows it to learn a new attractor, to develop a new attractor. And he's quite clear in distinguishing this from the kind of development that we see in the weights of a neural network, although I'm not convinced this could never be done in a neural network. I don't know. But it provides a way of understanding the crucial and perplexing role of the brain in the process of sensory evaluation of the world, not as if the brain were an analytic machine, neither analyzing nor interpreting nor representing the world, but rather reorganizing itself as a function of the entire history of the animal and its encounter with the world. So it's a strongly empirical kind of way of viewing nervous systems, and watch this space, I think, in future.